Okay. Hello, everyone. Welcome to episode 19 of Warsaw.ai. Thanks for coming. My name is Paweł. I'm one of the organizers of this event, together with Kacper, Marek, and Tomek. Today we have pleasure to host three great speakers. Agnieszka Mikołajczyk-Bareła will be our first speaker and will tell about TRURL.AI. Yes, it's a first Polish alternative to ChatGPT. Sounds very interesting. Then Cem Akgul will tell about AI in gaming, the good, the bad, and the ugly. And finally, Liron will join us, but remotely from Zoom, from New York City, in fact, and will tell about leveraging large language models for enterprise usage. And finally, there will be after party, so we invite you to stay with us. There will be sushi at the end, as usually. So we hope you enjoy this event and have fun. And I think we can invite our first speaker. So Agnieszka, if you're ready, the floor is yours.
Okay, hi, my name is Agnieszka Mikołajczyk, and today I will tell you a bit about TRURL.AI, the first Polish alternative to ChatGPT, which we created in Gdańsk. So, at first, I will tell you a bit about large language models and ChatGPT also. I'm sure everyone knows about it here, but just a little introduction. And also I will explain you the training process of large language models, talk a bit about open source alternatives, and also common challenges and issues in large language models. So at first, as everyone knows, ChatGPT is, somehow a chatbot assistant, which is designed to follow instructions or politely answer questions. And as its heart, we have a large language model. We call a model a large language model if we have over 1 billion of parameters. And since the emergence of those large language models, we saw a little bit of a shift from doing one task per model to many tasks for one model. So what is TRURL.AI? So this is it's a model alternative to ChatGPT, which was trained on both Polish and English. And unlike ChatGPT, it can be installed on premise. So this is like a bit of difference from ChatGPT. And we train it on speech transcripts and also conversations for business purposes. So we wanted to help agents make better calls and so on, and also to evaluate conversations. Additionally, it can speak and talk because we have our own ASR and TTS and engine. Okay, so how the training process of such large language model looks like. So usually we have 3 stages. Those stages look like how the ChatGPT was trained. So first, we usually train it for next token prediction. So how it looks like. So this is a kind of self-supervised training. So we have our big text corpora and put one piece of text and try to predict the next part of it, token by token. So a token is a subword. Usually one word is 1 to 3 tokens. It actually depends from of the language we use, but also how long is the word. So first part is token prediction. Then we have instruction fine-tuning and reinforcement learning with human feedback. Okay, so as I told you, in the first stage, we are going to predict the next token. So we are training the model in a self-supervised fashion. So first, we have to select our architecture. Then we have to prepare a large collection of text. So usually we can, scrape the whole internet and train the model on that. We don't need any labels because it's a self-supervised learning. Then we are training our model to predict the next word, and as a result we have a large language model that can write but does not respond to instructions very well. So this is the first step. But actually training such a model from scratch is extremely expensive. So some sources say that ChatGPT was trained on 10,000 of GPUs, which is a huge amount, impossible for a small Polish company to achieve that. So we have to have a huge infrastructure. But actually, the solution is we have lots of open source models, and in Voice.AI we also used an open source model. So I listed a few open source alternatives which you can find online. So one of the most famous for now is Llama family. So family of Llama models were published by Meta, so previously known as Facebook, under a non-commercial use. So this is a family of models which cannot be used commercially, but they are very popular because they work very good, and also they were one of the first published. And they include models like alpaca, vicuna, koala, and also wizard, so the whole zoo of models. And they come in sizes in 7, 13, 30, and 65 billions of parameters. So the Llama is basically such a model which we can use to fine-tune it later again. And one of the best working from this list is vicuna and wizard LM, so you can maybe try it at home. The next family is GPT-Neo. So those models were released by TRURL.AI. They come also in very different sizes. So this type of model is actually open for commercial use. So any company can use those models. And we also have Falcon. This one is a relatively new model, which also can be used for commercial use. So at first they published it and they didn't allow for commercial use. But actually later, because public was not very happy, they changed it to commercial use. And also some other architectures, less popular than the ones above. And 6 days ago, there was published new Open Llama for commercial use. Some company trained a model based on Llama architecture from scratch and published it for commercial use. Okay, so we have model that can do next token prediction. So we have model that just talks, and we can fine-tune it for instruction to follow instructions, to answer politely. So here we have like classical supervised training stage. So we have to collect lots of data in the form of prompt and response, instruction and answer, and so on. And we have to, we can take the model from the previous stage, from next token prediction, and fine-tune it for instruction answering. And here, the data collection is very expensive because we already have a model. We can just fine-tune it for maybe a couple of weeks, but we have to have like high quality data and lots of it. So we also have open source data sets. We have ShareGPT, for instance, 90K conversations of users with ChatGPT. So this is semi-artificial data set because we have prompts from users, but also answers from ChatGPT. And we also have Alpaca, Dolly, Open Assistant, MMLU, and Owca. This is a Polish translation of Alpaca dataset. Okay, so we have some of those datasets, but they are not very good. Sometimes we have problems in those datasets. So we have also hallucinations just inside of datasets. So we have to train our model, but our dataset is not very clean. So this is an example. We have instruction: classify the following shape according to simple geometry, and picture attached. So what kind of shape it might be? So obviously, we would expect that model will answer, I cannot determine the shape, but the answer in the data set is triangle. And we are training our model to learn that. And also we have sometimes just simply wrong answers, like here, convert 25 meters to kilometers. 25 kilometers. So obviously the answer is wrong. And some sources say that in alpaca, about 80% of math problems are estimated to have incorrect answers. 80%. Also, we have just problem with bad instructions. So the prompt is just nonsensical or graphic related. Like here, freeze the following sample of yogurt for 10 minutes. Yogurt sample. So yeah, no input. So this is from the dataset. Also, we have just grammar or stylistic errors. They are not necessarily wrong, but the data is low quality, and we are still training our model to predict the low quality data. So, for example, here we have an answer without any bullet points. Its sentence doesn't end with a full stop, or sometimes starts with capital letters or not. And we also have some biased answers sometimes. So here in Open Assistant, we have a question, which one is better, OpenAI or Open Assistant? Open Assistant, as it is actually open. This is the answer from the dataset. Also, sometimes automatically translated dataset can generate additional errors. So this is an example from Polish dataset Owca. It is an alpaca translated to Polish. So we have multiply 4 and 7. And the answer is, sorry, but I have not received any text to translate. Please send the text and I will try to translate it. Yeah, so this is the answer, which is actually in the dataset. And we estimated there is around 10% of such responses. So it's pretty bad if you don't catch it in time. Also, some outputs are empty, like the one above, or we have inconsistent input. So like here we have input, which is no input in different formats. So it's also might be difficult to catch. Okay, so how we addressed it when we trained our TRURL? Of course, we just did first careful data examination. So what I showed you here, some of them we didn't notice at first. So after a training, we noticed that our TRURL is responding to us, sorry, I can't translate that, and we didn't know why. And this is how we found out the following problem. So we did some automatic filtering, but also we used annotators to correct our samples, which is actually a quite expensive procedure because we manually correct data. But you could also use a cheaper solution using OpenAI GPT to evaluate this data. And also we did some custom data sets. So we have lots of data in VoiceLab.AI from ASR and other NLP data sets from transcripts and so on. So we prepared it for, like instruction, prompt, and answer type, and also corrected some company conversations with TRURL. So we used lots of custom data sets. Okay, and we also have the last stage, reinforcement learning with human feedback. So ChatGPT also used another stage to improve the chat even more, because the first stage, you train your model to have a model that can respond to instructions. But some answers might be written better because reinforcement learning lets you to have better answers. So we are using the last model to generate responses to another set of prompts. And we generate responses. For example, for one prompt, you generate 3 to 6 answers, and then we can rank them. So from best to worst. When we have such rank, we can train a reward model. So next step, if you have those ranks for set of prompts, you can train a reward model, and you can train your model from the previous stage using a reward model that will automatically tell your model if the answer is bad or good. So this is how the reinforcement learning with human feedback stage looks like. And this training is done with PPO, algorithm, proximal policy optimization, using the trained reward model. Actually, TRURL is just those two first stages. We read some papers that when you have good quality data, it might be enough to stop at the instruction fine-tuning, but we also want to perform reinforcement learning in the next stage. Okay, we have chatbot, but what now? So now comes evaluation, because training is not a one-time process. It's more like, constant iteration. So we trained once, we test it, and we have to, correct our mistakes and errors. So after each iteration, we evaluated our models, and we did it ourselves, but also we had a data science team which supported us in that. Additionally, we compared our results with different large language models, open source models, and so on, because we wanted to know if we did something wrong in the training, or this is a general problem in large language models. Actually, the biggest challenge was learning Polish, because most models are designed to speak English, with tokenizers designed to English, and so on. So what were the common challenges? Of course, lack of knowledge. Here you have an example, list the types of Pokemon. 10 types of Pokemon can be listed: Dragon, Main, Menacing, Hay, Bloody Forest, Metal Ninja, Psychic, Roman Cat. And this is the answer from Dolly model, open source model. Also, there are lots of problems with overgeneration. So this is a koala model, very popular one also. So the same question, list the types of Pokemon. Here are some Pokemon that could be used in Pokemon-themed game. Mewtwo, Mew, Mewtwo Wario, Mewtwo Wario Wario, and so on. And it continued like for the next lines for a very long time. So this overgeneration looping is also very common. Sometimes models just don't know when to stop generate text. Also, we can have some problems with context. So it happens when the model, for instance, does not take the context, does not respond to the context, or the other way around. So we have some context and we change the subject, but it still responds to the context. So here we have example, write me a code to import BERT model in PyTorch, and Open Assistant wrote some code. And then we wrote, write me a poem about ship in cosmos. And what Open Assistant did, he wrote the same code again, but changed the class from BERT model to Cosmos model. And that was it. So it took the context too much. Also, we have grammatical and stylistic errors. So here we have, hi, how are you? Hi, I'm good, thank you for the task. How can I help you? So we have lots of problems with grammar, especially in Polish. And also math. Math is pretty difficult for large language models because, this is a language model. It's not a math model. It might calculate you something because it saw it in data, but it still have like a very long list of probabilities when it's predicting next token. So even if we give it a task, 2 plus 2, it still have like large list of possible tokens with probabilities, and it's of course higher chance that it will find the answer 4 than 5, but still, I think many people on the internet wrote 2 plus 2 is 5. So there is still a chance that we'll get a wrong answer. So here we have example, answer the question and say how many words it consists of. Question, 2 times 3 plus 3. And the answer is 9, so the calculation is good, but number of words is 1. But in the question we have 1, 2, 3, 4, 5 words. But why errors are more common in Polish? So we think that it comes both from training data, from quality and quantity. Also tokenizers, as I told you before, are developed for English, not for Polish. The response generation also, because our models see less Polish data, the response generation is not much in favor for Polish language. Because when we are training our model, when we have trained model and we have, you know, the response generation process, we have a very large, long list of possible tokens with probabilities for each, and we are randomly selecting next generated token. So when our model didn't see much of data during the training, it might have shorter list for randomly choosing the next token. So that's why certain tokens gain higher probability and the answer might be looping and gaining some errors. Also, the type of data is important because we can, you know, use Wikipedia to train our model, but it will be question answer and it will not be a real conversation. So this is a different type of data. So how we addressed it? Basically, again, with data, we were spending really lots of time preparing the data, correcting the data. It was, again, not a single process, but we were correcting it over and over and over, because every time we tested our model, we saw some new errors and we corrected it, new errors, corrected it, and so on and so on. Okay, so to summarize, we encountered many challenges in data models. And so we had to develop our own additional data sets, especially in Polish. Also, we added business data. So for instance, speech transcripts or conversation data sets and so on. We successfully trained TRURL, which can be tested on TRURL.AI. So you are welcome to go and test our demo. And here you learned a bit about large language models training process, about open source models and data sets, and also about potential limitations of existing solutions. So thank you very much. Any questions?
Thank you for the presentation. What would you say would be the next step to further improve the model? Is it still more data? Is it better tokenizer? Is it change of the architecture? What is it?
Okay, thank you for the question. Yes, I think all of the above. So we are still working on data. Actually, we are just planning to run a new training on Monday. So we are working like crazy on those data sets now. But also we want to perform reinforcement learning in the later stage. And we want to test other open source models, because we tested a few now and we are still testing. We want to test all of them and see which one is the best. And also we were thinking about changing the tokenizer, but we don't have now it on our schedule, maybe later, but it's a good idea.
Okay, next question.
Hi, great presentation. And I have a question. If you've tested, if you've fine-tuned it on the business data, have you checked if it's not leaking? I mean, if you cannot retrieve it then when someone's using the chat.
Okay, so you are asking a safety question like that. So if some person can get out our training data. So we didn't actually test it because we anonymized all data. So we didn't use any business data from our clients, but we used our data sets anonymized. So every name is changed, every place is changed, every number is changed. So I hope it answers your question.
Okay. I think we have time for last question, maybe. Okay.
Thank you for the great presentation. So I have a question about like fine-tuning strategies that maybe you have checked few of those, like fine-tuning only some layers or doing some tricks. So yeah, what have you done here?
Okay, so actually we trained our model, like the whole model. We didn't freeze any layers. So we are training the whole model each time. We tried some quantization techniques, but it didn't work well for us. So it was a really high difference in in the quality of the model when we quantized it. So we actually just trained a full model, and we checked datasets training, because actually what we found out, if you train it on a very small dataset, like one dataset, it really fast catches this dataset. And we've seen like very great problem in catastrophic forgetting. So when we train it on one dataset, it actually start to forget everything else. So it was pretty difficult, because introducing a new dataset meant that we have to retrain it on a whole database of datasets. So it was pretty difficult. Also, if we had some problems with like end tokens and such, so oh, it's a whole story about how to train it.
All right. So if there are more questions, there will be time during the after party, because unfortunately we have to move on to the next speaker. So let's thank once again Agnieszka for a great presentation, and for coming here from Gdańsk. So I hope that Agnieszka will stay with us for the after party, at least for the beginning. But now it's time for our second speaker. So Cem, the floor is yours.
Thanks for having me. So today I will be talking about the AI advancement, which the effect on the gaming industry, basically. So first of all, I would like to talk about what kind of like a parts is included in the game development. And these are the stuff like the storytelling, game mechanics, and these are already like I will not touch to these topics too much, but I will briefly give a few sentences about the storytelling. Basically, you can make a layout of kind of like a rough sketch of the story and provide to an LLM to generate more details and just prolong the story and use it like this. And the game mechanics, there are softwares like Unreal Engine that really helps quite a lot to develop the game. And the rest of the speech, I will be focusing on the animation, graphic design, and user experience part, basically. So first, I will start with the characters in the games, and at this part, with the use of designers, it takes a lot of time to work on every single detail. But it is not only that. Once you have the mesh of a character, then you need to be able to make it move. So you need to transfer the motion on top of the character, and for this you need a rigged and skinned character which will react to the motion. So you can see that on the top left there is the old technique, which is linear blend shaping. Basically it uses the skeletons, and you can see the skeletons on the bottom image, like how it looks like. So these are our parameters that we are trying to control the meshes. And with the old method, so the skin was attached to the closest bone with a linear fashion, that there was no weights or coefficients. So every time when you were moving some sort of bone, the whole surface was reacting in the same way, even though a skin can deform in a different magnitudes depending on the material, etc. Or in the skin, if it's close to the muscle group, then it will deform more. And okay. So for this, already like an old solution exists with the AI that when you provide a mesh, it calculates the skeleton and the weights for the motion to deform the skin and the surface geometry. And for this, like they were using some sort of approaches that in the first part, and like this is like a module-wise end-to-end solution framework. And basically, in the beginning, when you provide the mesh, and these are already pre-trained models that they try to capture, they try to make calculations on vertices of the mesh to distinguish which are useful, which are not by, because like this model also has some sort of like a mesh attention, and this what mesh attention does is that it just compares the vertices to the other vertices and then distinguish which are important to figure out where the joint position is, because not every vertex is necessarily important to distinguish where is the joint. And by forwarding this information inside of a loop, and we are deforming the mesh, like a shrinking, to make them more dense to figure out the joint position. So in this case, later the solution makes some sort of clustering, and with respect to this clustering, it uses the most dense positions and accepts them as the joints of the mesh. Once we are done, we got the joints of the mesh, so which is already quite good. These are the most important parts of the body that we will parameterize our mesh model to like transfer the motion afterwards. And then there's the question. So we need to attach this like a joints to each other because they are affecting a certain area, not only point-wise. So for this, the solution uses graph neural networks to basically distinguish which joints are related to each other and which are not. And we just want to make connections between the relevant joints, basically. So they are using some sort of minimum spanning tree to distinguish where is the root node, because all of the calculations later will be started from the root and passed to the leaves of the tree structured skeleton. And later we have the bone, as you can see, and the joint positions. Then we start the skinning, and this is a this is a supervised model. So they had a big corpus of mesh data with the skeleton and the skinning ways prepared by artists. So they were this solution provides quite good, acceptable, and ready animation-ready models. And the next part is the NPCs, non-playable characters in gaming industry. Most of the time, like the NPCs takes quite a long time, but they have only pre-written script, so they can only tell a certain amount of like sentences, so nothing too fancy. So you can't make a casual like a chat with one of the NPCs in the game, basically. So in this case, with the help of the LLMs, you can improve this to be able to interact with the NPCs in a better way, and they will be more responsive, and they will keep the track of the context that you are talking with. So it is pretty cool. And basically, how this works, because LLMs, they don't really have a self-reflection mechanism. So when you ask a question, they are good at generating an answer, but they don't really check if the answer is correct or no, or they cannot adapt if it's a good idea or no. So building on top of the LLMs, when we provide like a certain kind of concepts like memory and like planning and reacting on top of, we can achieve this. And basically, this is kind of like the solution tries to mimic the human brain, how we function, how we make plan and like react upon them. And if you think about the human brain, once we observe the environment, and upon environment we make some we come up with some like a thoughts, and then we think about these thoughts, if they are correct or no. If they are correct, we accept them and continue with them and make our planning with them. But in the LLM, it is not really in this case. We need to provide some like smart solutions to push the LLMs to make this self-reflection. So in this case, basically, this NPCs or the smart agents, which can be used in games, can be done via keep tracking the memory, and the memory is basically the observed environment that we put the smart agents or smart NPCs. And once we keeping track of the memory, and we need to retrieve the memory, but not every memory is important in certain context. So we need to be able to make some kind of like a weighting on this memory entries with relevance and how recent it is, and like how much we need to rely on this kind of memories. And this part is just the observation, that observations are passed to some kind of like a memory stream. And later, it depends on the scheduling, but time to time we need to do self-reflection. So basically, self-reflection looks at the memory stream and then tries to use LLMs to come up with the most important 3 questions that we can come up with this memory streams. So we are still using LLMs to like a self-function. And the LLM comes with good questions, and then we ask LLM to, okay, give me answer to these questions that you provided with the given memory stream. So then LLM makes a self-reflection, and we just put into the memory stream, and we have some kind of like facts about the person itself or the smart NPC. And later, upon that, we would like to plan and react on these plans. But the planning is also a little bit tricky. So this top-down approach is rather good, because at the beginning, when we create NPCs, we are creating a file which is personality traits, and these are not changing. So every time the model like makes self-reflection, also it includes this personality traits. And upon this personality traits, it comes up with like one main goal. And like this one main goal is complex enough that we can put into steps. So generate more like plans or like tasks for us. And later we are just like reacting on them. And in the meantime, it's a loop. Still, it gets the observations from the environment upon the reactions, and then it becomes interactive. And on the other side, the more computer vision perspective of AI that is improving the gaming industry is, for example, inspiration tool. So you can test ideas or get some inspiration to build on top of what you see from such models like Stable Diffusion. This is like a fact the artists are using like this right now. And also a generation engine. And if you can see the video, this is the theory behind Stable Diffusion, and it is really nice to observe from like some physical kind of event that you can see exactly how they build the Stable Diffusion. It's basically we are providing this like not random but like a planned noises in some certain like time steps, and later we are just trying to predict the noise, remove from the noise image, and in the end we are just hoping that we will get a good image. So it's how it works. And also there are nerves, but they are not really used as much as like the Stable Diffusion or like the mesh format in the games, because in games you would like to have a good performance, FPS score. So optimization is really important, and mesh right now it is accepted kind of technique in path in the industry. And like this is one of the approaches we were testing. So we are coupling the Stable Diffusion with the differential rendering to like paint the surface of our mesh for different looks. And if I can explain, so this is the second stage of the step of the generation. We already generated the first view, the front view of this character. And then we would like to generate a different like a view, so that in that we can do like inverse rendering, so that we can embed them to the texture map of the character of the mesh. So this is like if you see this image, this is the normals that we are seeing from this perspective, from this view angle, and the top normals are already seen normals, and we already generated some kind of texture for this normals. So when we generate the new image with the Stable Diffusion, we provide the depth maps, etc., to make the generation more stable and to get exactly the shape that we want. later we are comparing the normals and we are making some blending with the seen parts, and like we are just passing the unseen parts to the mesh and move on to the second stage, like the next stage. And if you can see, like this is the whole generation step of this model. So each time we are just rotating the model a little bit and making generation and try to blend the generated and already embedded views. Yeah. And yeah, this is the full result of this generation. But unfortunately, it doesn't work for everything. So there are still drawbacks in the stable diffusion, that because we are relying on stable diffusion to do the generation for us, yeah. And like this is an issue still, but because it doesn't really understand that it is like even though we are providing the same depth map, same seeds, it doesn't really understand that this is the same object, but we are just trying to look from different perspectives. So there are some like problems with it in like generating 3D assets basically. And there is one solution, like a smart way without any training required, to work on the classifier free guidance domain to fix up this part. And basically what we what this solution does, that maybe I can show it here, and it actually solves this Janus problem, multi-head problem, when you try to generate the same object from different perspectives. We are passing like in such kind of solution. We have the main prompt, and we are providing some negative prompts and assigning weights to them. So basically, what we are trying to do is that in the score space, when we are like guiding the generation during the inside the stable diffusion, we are trying to find the embeddings of these negative prompts, but we are trying to make this amplification or like to the direction of the main prompt as a like a distribution. If you think as a distribution, we are trying to arithmetically find the combination, like a product of these prompts in arithmetic way to improve this. And as a summary, so AI is changing quite a lot of stuff in gaming, and mostly it is just reducing the production time so that the game from the concept to the market, it is like shortening like rapidly. So this is the biggest impact of the AI in gaming industry. And if you will have any more questions, we will be here after in the party as well. But thank you.
All right, questions.
So thanks for your presentation. And I have a question. Which solutions you presented are good enough to be computed at real time during the game?
For now, none of them. Yeah, like it is immature still. Like it will require some time to like make them mature as a solutions to generate assets in the games. But this is about the generation part. In like if you would like to make like an open-end game, obviously it can't be real time. But if you're only working on the parts of the game, like assets or like a scene, they are all pre-calculated and just compiled inside the game and optimized. So like this doesn't really affect, but as you know, like an open-end game that you want to make it real time, there is still some time.
All right. Do we have more questions?
Hi. So you talked about one of the options is to generate responses for NPCs, and how safe is it now in terms of, for example, a player, I don't know, getting secrets from an NPC that should not know those secrets, but the model has them somewhere, and how safe is it? How usable is it? And yeah.
I mean, like we mostly focus on the graphics part than the language part of the design. But yeah, it is like a valid point to consider about it. And make the like restrictions in like the language model to operate with the players. Like it's true. I can't really tell exactly how it will be done since my focus is on mainly on the graphic design part. But yeah, it's a real challenge, I would say.
Okay, great. We have time for maybe one or two more questions. Okay.
Thanks for the presentation. So I have a question about stable AI versus nerves, because for example, like if you want to create assets, then maybe nerves will be better because they have some geometrical understanding. So the question is like, have you compared those, or like what are the advantages of stability AI? Yeah.
I mean, in general, the game development is based on the mesh assets, because then you can use like a PBR, like a based rendering, which is quite optimized right now. That like it runs, it has good performance. But in nerve domain, like just running on the nerve and like generating everything, there is like no game engine for like supporting it right now, as far as I know. And beside of that, if you just want to like generate a nerve and then transform it into mesh, so this is quite a challenging like a task to do, because like every mesh has wires and the topology quite matters, like when you prepare the skinning and the rigging and overall realism. So because of this, I guess the mesh is more followed by game developers than the nerves right now. So nerves are mostly experimental at the moment, but like they have better quality if you are trying to generate the 3D asset from like a 2D images. So they are good at this. Yeah.
Okay. Maybe last more question. Okay.
Thanks a lot for the great talk. I actually wanted to go back to the first question about the real-time stuff. So how long, is there a lot of interest in like getting those things to work in real time? So like having, you know, an open world where the character can essentially, the animation can be adapted to any obstacle on the fly. Is it something that actually people are trying to get to work, or is it more like, you know, something that maybe few PhD students work on? So that's like part one. And part two, if it is something that would be interesting to the gaming industry, how far away from that we are, do you think? Is it like more like 3 years, 10 years, or it's like just, you know, not even, you know, or is it just so early that you cannot even say how far away it is?
I mean, like maybe I can start with something funny. Moore's law is dead, so like there won't be a huge increase, I guess, in the compute with a given like a volume. But I can't really estimate, since like it is not exactly my domain, or like I am focused on this part. But like if I can make some kind of like estimation, yeah, I think there is still quite some time needed for this to be done.
So we shouldn't expect it to be in the next Assassin's Creed game.
It will be a hard task to for developers to do, I guess. Yeah.
All right. So let's thank Cem for this great presentation.
Thank you as well.
You. All right. So it's time for our third speaker.
Great. So first of all, great to be here. Thank you for giving us the opportunity to speak a little bit about what NVIDIA is doing these days, especially in large language models. My name is Liron. I lead what's called the developer relations at NVIDIA for Central and Eastern Europe. And basically the past 5 years, I've been working with the ecosystem, understanding their AI workloads, understanding where the pain points are, how to accelerate, how to optimize AI workloads, specifically deep learning AI workloads that are running on GPUs. And I think we all know generative AI is kind of exploding. It's been Very good few months for generative AI. We all see the adoption of ChatGPT and how quickly it's going. And we also see past ChatGPT, how many new large language models and generative AI models are coming out. And I think, there's consumers who consume these large language models and are doing things with that. But I think us as data scientists and developers, we need to find what's the next big use case. What can we do with these large language models in different use cases? So what we're seeing a lot in terms of use cases is a lot of companies are doing text generation, for example, marketing copies, or obviously summarization. Translations are going very, very well. Coding, auto coding is something big, and I think it's going to change a lot of the developer world. Image generation, obviously, with DALL-E and all these image generating neural networks that are coming out. And life sciences is actually going through a huge transition, in my opinion, especially in the drug discovery world. We're seeing large language models that are learning chemistry language, biology language, and we're seeing a lot of workflows in life sciences that are alternating the way they work. And this is an area that hasn't been touched for years and years and years. And all of a sudden, the workflow for drug discovery is getting a lot shorter, or I would say easier, because all of a sudden there's automation around the drug discovery processes through large language models. So a lot of things are changing, a lot of new use cases, but I think for a second, let's see what happened. Okay, what caused this? So I've been at NVIDIA, like I said, a little bit over 5 years. Mostly in the beginning, we were talking about vision, video analytics, and around mid-2017, a new architecture was unfolded, which is called the transformer architecture, which kind of brought a breakthrough into the world of NLP. And the minute the paper was released about this new architecture, lots and lots of researchers started testing out this architecture. And a year later, we were introduced to BERT, a large language model. The first one, I think, that made a big headline in what you're able to do in terms of language models. And from then on, we just saw more and more models coming in until about less than a year ago, ChatGPT kind of broke through, as well as DALL-E with the image generation, as well as data science, life sciences. If you're familiar with AlphaFold, became a big breakthrough. So I think in the past year is the big bang of large language models. But I think it's important to see a little bit historically what happened, how did we get here? And we see how these large language models just kept getting better and better by adding more parameters and the language models becoming bigger and bigger. So what is this transformer architecture? Like I said before, transformers, we were mostly dealing with convolutional neural networks and reoccurring neural networks, RNNs and CNNs. RNNs and CNNs were good at very specific language tasks because they had the ability to go into loops, and that loops gave them the ability to kind of have what we call a memory. So they were able to take a sentence and kind of make the context of the sentence and then complete sentences. But where they failed was once there was more than just a sentence, there was a paragraph, and they weren't able to do the context configuration that's needed to perform sentences. And basically they were missing what we call memory, okay? The memory of the context of a certain word that they'll be able to answer it correctly. So that was RNNs. And then came LSTMs, if you're familiar with that kind of architecture. And LSTMs, they brought another breakthrough because they were able to give context some sort of memory. But again, this was all very limited because there's only so much quote unquote memory in loop architecture of these neural networks that was able to be dealt with. And so when the researchers took the CNNs and the RNNs and the LSTMs and thought of a process that would allow this so-called memory into the neural network, they came up with the transformer architecture. And basically, if you look here, there's a mechanism called self-attention, where when the data was inputted into a transformer architecture, instead of looking through the vector of the whole sequence, they were actually able to give each word its own weight. And that gave them the ability to hold more and more and more memory. And that's when we saw the breakthrough of language models becoming bigger with more parameters. And the more parameters there were in the architecture of the network, the better the language model reacted and the better the answers were. And so when you take the encoder architecture, the decoder architecture, and the self-attention mechanism, and you put it together, that's when you get a transformer model that all the large language models today are built up off of this architecture. And that gives them the ability to be able to do the chats and give the long answers and take long sets of wording and putting thought into it. And this brought the big breakthrough. So large language models is great. I don't know, I assume some of you or most of you or even all of you played a little bit with ChatGPT or maybe Bard, or maybe use DALL-E to render pictures. I think they're great, and their breakthroughs and their ability to understand what you're saying and then answer you in context is something that was just not able to do a few years ago. But then comes the question of, okay, so there's a generative AI model. I want to bring it into my domain. So I need to fine tune it, or I need to make it better in my domain. So there's all kinds of customization techniques for generative AI networks. First of all, there's supervised fine tuning. So that means you have a lot of data in your domain and you want to retrain the large language model with that data so that it'll be really, really good at your specific domain. You can also do incremental knowledge. As the language model is working, it learns from examples that you're going to give it. You can have continuous knowledge, where this is the human in the loop. The human in the loop will always tell the language model, hey, you're doing great, or no, that's the wrong answer, let me teach you. And of course, there's language models that we want to give runtime knowledge. So we want, for specific use cases, language models that will be able to be connected in runtime to large either corpuses or databases, so that the answers that they will be given will be correct in runtime. So there's a lot of things that when you take a large language model and you take a base, a certain base that you consider your base, you have to run processes in those large language models to fine tune them or make them specific to your domain. So I do want to kind of go through example of what it means to fine tune or correct your language model into your use cases, and a little bit of the definitions of how we see it. So first of all, there's zero shot. This is an example of a 530 billion parameter language model that we took as is, and we ran it on an article and we asked it to summarize it. No touching, no fine tuning, no transfer learning, no retraining. So sometimes you want to take a language model and you can work at it as is, and it's fine and it's good for your use case. Sometimes with what's called the few shot learning, you're able to give it just a few examples. This one specifically, we gave a 530 billion parameter language model, just one example. And they're already do the task even better. And this is called the few shot learning. And then there's p-tuning or parameter tuning. This is when we still don't want to retrain the entire model from scratch. We want to take the model as is, but through parameter tuning, through prompt tuning, a specific language that the model will understand once you give it hundreds and thousands of examples, you'll be able to get your language model pretty fine-tuned to your specific domain. So let's say if you want to take a language model and make it good at Q&A, okay? And your end users will give it a question, and the language model will answer back short answers. That's something that you can p-tune it into doing. I think it's these three, what's easier, quote unquote, about them is that they are all inferencing type of learning. So when you're inferencing with the language model, you're doing zero shot or few shot or p-tuning. You don't need to retrain the model. This is all happening at inference time, and you just need to learn the right language in the prompt of your large language model in order to get it learning. The last type of learning is, of course, fine-tuning. So if you have a lot of data and you have a very, very, very specific domain that you want your large language to learn, this is when you're going to need to retrain it. This is when you're going to need to take the architecture, the weights, everything from your large language model and actually retrain it with all the data offline that you have for your domain specific. And I think it's important to understand these four types of examples because according to the use case that you want your large language model to do, you need to know what kind of customization is the right one or the easiest one or the fastest one for your language model. So these are the four types of let's say, fine-tuning, relearning, retraining your language models that we see today. On top of actually wanting to reteach your language model or to fine-tune it to your specific use case, there's many types of challenges. And I think it's important to understand the two types of use cases that we see in generative AI models. First of all, the use case of building your own foundation model, building your own generative AI model from scratch. First of all, you need to understand what architecture is the right one for your use case. You need to get all your data together, and you probably need a lot of data if you're going to create your own foundation model. You need technical expertise, and of course, you need complex algorithms with big GPU clusters. The other option or challenge using just the foundation model, like we talked about, fine-tuning it, is, again, it doesn't contain a domain expertise and you're going to need the time to fine-tune it. It's not easy, or it's not trivial, for taking a language model and making it correct for runtime. And we call it frozen in time. I think we all see it with ChatGPT, right? It's not always up to date with everything that's going on. And it's hard to get these large language models being constantly updated with the right data. And of course, bias and toxic information, we'll talk about it briefly at the end. We want to try to secure these large language models as best as possible. So I did want to tell you a little bit of what NVIDIA is doing in order to kind of help data scientists overcome these challenges. So what NVIDIA created is something called the NeMo framework. NeMo framework basically is an SDK open to developers, data scientists. It's open source, or some of it is open source. And it takes you through the entire pipeline of either retraining or fine-tuning or p-tuning your language model. So if you look at this, picture, you can see all the steps that a data scientist needs to take in order to take a large language model and make it its own for its specific use case. So first of all, you have the data curation, which is a very long process. Think about gathering all your data. You have to deduplicate all the duplicates that you have in your data. You have to annotate, or you have to label your data. So there's a lot of handling of the big data that you have in order to create. So within the NeMo framework, there's a lot of scripts that help you automate all these steps that you need to do with the data. Distributed training. So it doesn't matter if you have A100s, H100s, L10s, A40s. We've got so many GPU types out there with so many different clusters. The one thing that's for sure, you're going to need to distribute your training if you're retraining your large language model. And this SDK will help you do that. So it'll help you understand the cluster that you have, how many GPUs you're running on, what kind of memory these GPUs have, and how to best train these transformer models on top of GPUs. Of course, the customization, what we spoke about earlier, depending on what type of customization you're doing to your large language model, there's automations and scripts within the framework. And guardrails is something that I'll briefly talk about at the end, but guardrails basically gives the ability to secure your large language model so it doesn't start doing things that we wouldn't like them to do. So that's the NEMO framework, and that's for mostly people who are going to retrain foundation models or create their own foundation models. Obviously, there's a lot of services out there. We see ChatGPT services, we see other companies giving out their APIs and letting others use their language models. Obviously, NVIDIA has also this type of service. So on top of the framework that we also have the NEMO service. We have the BioNEMO service. If anyone's in life sciences, we've been working very, very hard with the drug discovery community and ecosystem in creating biolanguage models that are correct for the drug discovery pipelines. And Picasso services for image generation. So everybody doing vision transformers, this would be a great service for them to take. Again, like I said, this isn't only for large language models. We see a lot of image generation also happening. Things like diffusion models, if you've heard of them. So these diffusion models are what's been able to do the big leap in computer vision and in image generation. And here too, these large image generation models aren't the easiest to retrain, aren't the easiest to sometimes use. And so within the NEMO architecture, we know to give these special scripts and automations for large language models, but also for the image models. Here you have the list of the language models and vision models that we are able to support out of the box today. So if you want to fine tune, or if you want to retrain GPT or T5, which is an encoder and decoder, or BERT, you'll be able to do that through the framework, and it'll give you a really nice automation and boost on top of the GPU cluster. Same with text to image models, right? Stable diffusion. If you're from that area, you're definitely familiar with that type of model. So you can take it and retrain it. And of course, image to image. I did want to say a few words about guardrails. So again, security is a very important topic in large language models. We're all aware that toxic language is something that we all want to get rid of. And so what NVIDIA released lately, and it has nothing to do with the NEMO framework, it's a standalone SDK for whomever wants to put in what we call security guardrails within its large language model. So it doesn't matter if you're going off of NEMO, taking a language model off of Hugging Face, you can use NEMO guardrails in order to put in safety and security within your large language model so that inputs from prompts are being checked, and also outputs from the language models are being checked to make sure there's no toxicity, there's nothing going on that you wouldn't want in terms of security in your large language model. I think, so that's specifically what NVIDIA is doing in large language models, but I did want to take a minute because I think sometimes it's missing in the knowledge of what NVIDIA is doing these days. So everybody knows our GPUs. Everybody knows it takes a lot of GPUs to train large language models, generative AI, or just regular vision models or video models, for those of you doing video analytics. I think what NVIDIA is really good at is understanding the AI pipeline and understanding where it needs optimizations, where it needs a little boost of acceleration. And so what we did is we took this entire pipeline and created SDKs, by the way, open source, and I'll tell you where you can get them, but also available on GitHub. And for each of these steps, we created automations or SDKs or accelerated libraries, something that will help accelerate or optimize your work. So whether it's taking data, and it could be vision data, right? Like if you take a look at healthcare, we have MRI, CTs that are very, very large, or genomic data that's very, very large, or videos that are very, very large. So taking automations and helping place this data right into the GPU memory so that in the pre-processing, it'll go a lot quicker, or training and validation workflows that can help you accelerate your work. So basically what we say is we know our GPU is the best. Use our automations to help accelerate and optimize your work. And so what we have are workflows. So we talked about the NEMO workflow today, which is LLMs, but also conversational AI. We have many, many different workflows. Either it could be data science workflows and it could be industry workflows. But the point is we have something called the NGC catalog. It has containers, it has pre-trained models that you can retrain. It has workflows for pre-processing or post-processing. We have SDKs for accelerating inference. And what we do in our day-to-day is actually work with the companies and with data scientists to introduce them to these accelerated libraries so that they can implement them in their work. And like I said, most of what we do is open source. We're getting to the end, so just a brief note about how you keep up to date with all this stuff. We have our developer program. Happy if you guys can join it. This is the way to stay up to date with everything going on at NVIDIA. So when you join the developer program, it asks you, what are you interested in? Robotics, healthcare, LLMs, generative AI. You can pick and choose whatever you're interested in. And that's how you get up to date with webinars that we hold, with new SDKs that are coming out. You can download the SDKs and get all the information about the SDK. So it's really great to be in touch with everything that's happening in AI and GPUs. And if there's any startups out there, we also have a starter program. Basically, no T's and C's. It's just a program to manage all the startups that we're working with. If you're working with GPUs and you're working on top of our platforms, I do suggest that you join the Inception program. You get really good technology support. You get developer relations guys that are industry related like me that can help you accelerate and implement your work, both for training and for inferencing. That's it. Thank you for listening.
Great, thank you. All right, do we have questions to Liron?
Yeah, hello. Great presentation. So I have two questions. First of all, could you say a few words about NVIDIA's strategy in the context of AI? And second question, could you say a few words about NVIDIA's competitors in AI? Thanks.
Sure. So listen, in terms of competition, we embrace competition. I think that's what makes us run faster. We see different companies coming out with different strategies and different hardwares. And I think from that point of view, the more the merrier, but we're good at what we do. GPUs have been around from the beginning. They used to be, their old use case, quote unquote, was graphics. And from there, we still are the #1 in graphic processing. But we just found out that they're really good at AI. And so I think we have the leverage of all the software that we have. But like I said, again, competition is a good thing, right? It makes everyone be better at what they do. And so we embrace it. And we love that AI has become such a big ecosystem. I think it's great. In terms of our strategy, again, I think, I don't know if to use the word strategy, but what we've noticed is that AI is different in every industry, right? If you're developing a self-driving car, then the AI that you're developing for that self-driving car is going to work and inference a little bit differently than if you're doing healthcare and you need to do anomaly detection in medical imaging and CT, MRIs, ultrasound. And it works differently if you're building a robot and you want the robot to open its eyes and know where it is and know where it's going. And so I don't know if it's considered a strategy, but what we're trying to do is per industry vertical, create the right software stack so that it will be a lot easier for data scientists to leverage AI in that specific domain. And that's why today NVIDIA, by the way, is built as business units per industry. So a lot of industry units are looking to see what's going on in the industry, what kind of AI use cases are right, that's, we have cybersecurity all of a sudden with AI going into cybersecurity, and, generative AI is exploding in every industry. So again, what we're trying to do is create the right software stack per industry so that people find it a lot easier to leverage our GPUs. And again, GPUs are everywhere. So it doesn't matter if you're running on the cloud, if you're running on-prem, if you're running on the edge, and we have our Jetson GPUs, I don't know if you guys are familiar with it, that are edge devices. There's GPUs everywhere. So that when we work with our partners, we create the right architecture, and the forward thinking is, hey, how do we make this the easiest possible to implement?
Right, great. Thanks for the answer. Do we have more questions now? Okay, there's one more.
Hello. So I would like to ask about specific of learning of those language models, and I would like to ask a question: how much data is lost in specification training? So what we can do is we can kind of generalize first, and then we specify, as I understood you, and we can then specify towards a target domain, right? So how much data is lost, if there is anything lost during this specification training that you feed such a huge data from this specific domain?
So first of all, that's a great question. By the way, it's a question generally for models in general, right? And specifically for LLMs, it's even more tricky because like I said, for LLMs, you can fine-tune them in inferencing, where in other models, you need to retrain them. We get this question a lot, right? How much data is the right amount of data to retrain your model? And unfortunately, I don't have the magic answer. There are papers that give you some kind of indication according to your use case, what kind of data is needed. By the way, there's also so many types of retraining, right? You can do self-supervised training, where you actually have someone sitting and labeling the data, and then you work a lot more on the data preparation, but then the training, it becomes a little bit easier. And then you also have unsupervised training, where you just give the data the model a lot of data, and then they learn it themselves. And in each one of those types of training, the numbers are different, right? You need a lot more labeled data to fine-tune a specific model to that specific example. And you might, other way around. If your data is labeled, then you might need a lot less examples because you're already telling the model, hey, this is what you're going to learn. But if you want to make your pre-processing of the data easier, and you just want to give the model a lot of data and learn on its own, then you need a lot more data. So I don't have the magic answer in terms of, how many gigabytes of data or terabytes of data you need. It really, if you take a look at the different large language models, they always say what data they were fine-tuned on, what data they were trained on. And sometimes you need to find the model that was trained on the data that is closest to your domain, and just take that and fine-tune it. I can try to give an example from the life sciences. I spoke about the drug discovery large language models. So a lot of times what we see these chemical large language models being taken by researchers, and then just fine-tuning it to the specific chemicals that they need to run their runs on. So I don't know how much specific chemical examples they have, but I think I'm sorry that I don't have like the out of the box answer, but it really varies in terms of which language model you took, what your domain is, and what kind of retraining you want to do for that language model. Again, I think I'll just say one word about the p-tuning and that I was talking about earlier. In large language models today, the good thing is that you don't necessarily have to retrain the entire model. You can just do what's called prompt tuning. And then that means that you kind of teach it by the human in the loop, giving prompt tuning, giving examples on the fly. And sometimes that's enough. you don't need your own data to retrain an entire language model. So I'm sorry that I don't have like the out of the box answer for you, but it's just that the models are so varied these days for LLMs and, you know, for generative AI in general, and just for AI models out there. Sometimes it just needs a little bit of data for your specific use case. And sometimes you really do need that terabytes of data, especially if your domain is so specific. So the more specific you go, the more data you need to give the large language model to do your domain specific tasks.
Okay, thanks, Liron. Fair enough. All right. So Liron, thank you very much for just answering all the questions as well.
Sure.
Thanks for the great presentation.
Thank you for having me.
So we wish you are here with us, because now we'll have the after party and networking. So then people
next time.
Yes,
Next
people could ask maybe more questions. I don't know. Is there maybe someone who would like to ask very last question? Just the last chance. Okay. So two people has just raised their hands. So maybe we'll try once again. Okay.
Sure.
So thank you for your presentation. I have a question regarding this pre-prompting. You mentioned that it would be sufficient to provide hundreds or thousands of examples. And my question is, does this context stick when you ask multiple questions in this context? Or does the context fade? And I don't know, once in 100 questions, you should provide examples again, just to
That's a great question. I can actually check internally with our dev tech. From what I know, it pretty much sticks. But the main problem with p-tuning is how much your data is changing. So if, let's say, a few months down the line, you know, something drastically changed, and all of a sudden you need to update your model with this new data that's been formed, you're going to have to p-tune it again. But for specifically your answer, from what I know, the context knows to keep at it. So it's not like a constant p-tuning workflow. I think it's once enough, your model is tuned and you can go into production. The question is how often, and by the way, it's a general question, how often does the data that your domain-specific large language model is now working on changes? And if the data is changing all the time, then you're going to have to find some kind of workflow to keep on updating that language model.
Okay, great, thanks. So Liron, I'm not sure how much time do you still have, but I saw that there was one more person willing to ask a question. And there will be no opportunity to ask during the after party, so if it's fine for you,
it's okay.
Just allow, okay?
First of all, thank you. I wonder about mostly theoretical part, like for MML development. Like we are still looking for a nice theory for a basement, or we have already some nice theory and we can build something on it, develop something on it. For example, NVIDIA has a theoretical research group in the sense of philosophical and in the philosophical and linguistic sense, or universities are doing this and we are just keeping from them.
Wow, it's a tough question. By the way, NVIDIA has an R&D group, and I think some of them are also doing research in Warsaw, just so you know, for those who didn't know. I don't have the straight answer for that. I can tell you that NVIDIA research is working on many types of areas. I can tell you that I'm in touch with different professors who are also researching, all kinds of experimental things that have to do with LLMs. I can tell you one thing that I know. When I was in academia, which was a long time ago, I don't think industry and academic relations were as close as they are these days. And I think all the companies, the big ones today that you can think of, who are doing AI have a research group that's very close to researchers in the universities, and vice versa. You have researchers in the universities that sometimes even have a leg in these large companies. And so there are things that are going on in research in terms of, baselines, ethics, things like that. And if there's one good thing that's happening is that industry and academia are talking more than ever about this research. And hopefully, we'll see more things coming out that will help us leverage AI even better. That's the smartest thing I can say about the question. Sorry if I didn't answer this, specifically to what you asked.
All right. Great, thank you. So that was the last question. Liron, thank you once again for joining us. Thanks for a great talk and answering all the questions. That was very interesting and fruitful discussion. I believe we learned a lot. So thanks once again. And we also, I think we can finish and officially invite everyone to the after party.
Enjoy your after party.
Thank you. Thanks. Have a good afternoon.
Bye, everybody.
Bye-bye.